Hello, everyone. Thank you for joining us in this webinar today. It will be focused on high energy injection of remedial amendments. Our speaker today is Mike Masaris from AST Environmental. He's a senior remediation engineer based in Golden, Colorado, and he has bachelor, master degrees in environmental engineering from Penn University, and experience as a remediation specialist in many companies, including URS, Regenesis, and now AST. Probably more relevant for some of us, the ones based in Australia, is that he typically oversees the design and implementation of all high energy injection projects. And he will actually be here in 2 weeks or 10 days, because Mike is flying to Melbourne to join us at Eco Forum. That will be between the 10th and 13th of October, if I'm not wrong. So if you want to meet him, that will be a good moment for it. The week after, Mike, if you can put the next slide. The week after Eco Forum, we're very excited as well to be organizing some half-day workshops in different cities. We will be in Adelaide, Brisbane, and Sydney, and we'll be organizing these workshops on advanced technologies for site investigation and in-situ remediation. So if you are available, or if you're in any of these cities, please don't hesitate to register and join us there. You can use the QR code that you see at the top to access the registration form. The workshops will be totally free and will be from 9 a.m. To 1 p.m. In terms of the webinar today, will last around 1 hour. We'll have 10-15 minutes at the end for questions. And that's all from my end, Mike. Thank you very much for giving us some of your time today. And if you want to add anything regarding the workshops or anything else, please go ahead.
No, thank you. Thank you for the introduction, and thanks to everyone for joining us today. This presentation is being recorded, so we understand that everyone here is busy, and so if you do have to drop off early, this will be posted to YouTube, and Jonas will have that link that he can share out. Or if you'd like to share it with any colleagues, please let us know. So we'll go ahead and dive into it. Before that, though, I just wanted to just mention, which is, we're gonna have to, due to the time constraints, we really can't do a deep dive on all these topics. And so during the pandemic, we at AST gave a series of webinars, maybe 30 or so, and we posted all those on our website there. So you can just see there's some that are really specific to, say, LNAPL or DNAPL, fractured bedrock. So if you're interested, you can check that out. Check that out there, and we'll go into over the 4-hour format that we're going to have at the workshops that Jonas mentioned. We'll be able to get a little more detail than we will today. So Jonas covered most of my bio. So I did my university work and graduated 98 and 2000 from Penn State University. He mentioned that I started off my career as a consultant and then moved into the reagent side of our business, working for Regenesis. And then prior to AST, most recently worked for a company called Vironics, which was across the US, and they're structured very, very similar to Legion, actually, offering high-res services, so things like the MIP and UVOST, and as well as injection services. And so when I first got out of university and I was starting off as a consultant, I was really tasked with, at both companies, at pilot testing new technologies. And that's sort of where I got my initial experience in understanding reagents, pros and cons of different reagents, as well as pros and cons of different injection techniques. Because going back 23 years ago, they weren't really well understood. So things like radius of influence and injection flow rates and pressures and all of that. And we've come quite a ways, and that's sort of hopefully be able to convey some of that information to you here today. So skip down to 1, 2, 3, 4, 5, the fourth bullet down, sub bullet. So the bulk of my experience is on the bio side, so like on the aerobic and the anaerobic bio side, so things like ORCs to things like emulsified vegetable oil on the anaerobic side, chemical oxidation, so everything from hydrogen peroxide, sodium persulfate, sodium, potassium permanganate, that most of you are going to be familiar with, as well as chemical reduction. So things like zero valent iron. At AST, started working more with activated carbon-based technologies, which definitely falls into the slurry end of our conversation today. And then most recently with modified clay-based chemistries, and those are specifically used for PFAS sequestration. And we'll get into those. We really don't talk about technologies at all here today, but we will cover those in the in-person workshops. And lastly, from a geology standpoint, very similar to Australia, we have quite a broad range of overburden geologies, low permeability to high permeability, weathered bedrock and competent bedrock, and we'll cover each of those in the presentation today. So our roadmap, we'll talk about the differences between liquid and slurry injections. I would say in general, most folks are more familiar with the liquid end versus the slurry end, and matching up your injection techniques and your tooling, and this sort of extends to even the injection pumps that you use as well. Injection pumps are vary quite a bit from low pressure, low flow to low flow, high pressure, high flow. And so we'll talk about that a little bit. Talk about the differences between injection wells and direct push. We get these questions quite a bit, and there's pros and cons to both of those approaches. And something that we encounter quite a bit here in the US, and we've encountered it in Australia as well, is what happens when you hit if you want to use DPT, but you have DPT refusal, but you're not in competent bedrock. And so we'll cover that. We'll cover that case. We'll cover bedrock briefly, and then we'll talk about just sort of best practices from an injection design standpoint. And then if we've got the time, we'll wrap up with a few brief project summaries. So in general, we've got a handful of ways that we can apply reagents in the subsurface. So the first is going to be, direct push or injection wells. Most folks are going to be familiar with that. Each site, again, we're going to get into this a little bit, but trying to match up the site with your conceptual site model, with where the mass is, with the right technique, right? Whether injection wells make sense or direct push makes sense. We'll cover that pre-drill technique, which is that situation that I mentioned when you have direct push refusal, say into a weathered bedrock or transition zone. Bedrock, we're using straddle packers there, so we're not using wells in general to inject in bedrock. We're using straddle packers to isolate fractures. And then lastly, this is really truly the best way to apply any reagent is with direct mixing. We just don't have, on most sites, we don't have the opportunity to do this. But if you can mix any reagent in, you can't get better distribution or better contact than using that approach. And so on the right there, I've got an example of kind of what a cross-section would look like for a direct push application. So here, this is an example of injecting a slurry, and we're injecting it in lenses, top down. We'll get into sort of top down versus bottom up in a little bit. And so top down, you're injecting in these horizons. They're spaced about a half a meter apart, and you're staggering those intervals between your adjacent injection points. And you're designing your radius of influence such that you do get some overlap between the adjacent locations. So here's an example of what that looks like on the surface. It's a pretty small footprint. You've got a geoprobe that's tethered to your injection rig, your injection unit. Here's a sonic rig. This is the geoprobe sonic rig. And this is on a site where we were advancing down about 50, 55 meters to get into some weathered bedrock. So this is an example of that pre-drill application. So a direct push unit came behind this, and we'll get into that technique here in a little bit. We're talking about fractured bedrock. As I mentioned, we're using straddle packers. And so here's an example of the straddle packers that we use. They use the diameter once they're inflated is about 15 centimeters. And here's a photo. This is actually our first application of an activated carbon technology in Australia. It wasn't an injection. It was a soil mixing application out in Western Australia. And then lastly, trenching. So this would be an example of how you would install a PRB if you weren't going to use injection techniques. And I would say in general, if your groundwater table is shallow enough and you can get away with not having to use shoring or any sort of trench boxes, then the economics usually are in your favor to use this approach, assuming that you've got the room to do it. And usually you're mixing your amendment with something permeable, like something like a clean sand. So start off with, why do injection projects fail? And I think it really kind of comes down to, really a couple things. I mean, first off, all these chemistries that are on the market in general are going to work in a laboratory, right? So if you're going to go do a bench test, and we get asked to do bench tests all the time, and the bench testing has its place, but does that mean it's going to work in the subsurface? And the answer is absolutely no. Because if you think about it, when you're in a laboratory, you have a perfectly mixed system, and you're also using much more water than you are soil. So your soil to water ratio is pretty much inverted. You're using 2 to 3 parts, say, water to 1 part soil, which is really kind of the inverse of what we see in the subsurface. So definitely can check boxes as to whether you're going to have any sort of intermediate compounds or something like that, or if you've got a geochemical concern, and so you want to look at dissolved metals, say, something like that. Definitely has its place, but definitely you need to take that, and the next step would be pilot testing, which we'll sort of get into. But why these sites fail, I think first off, I think it's just a reagent loading situation, because especially when we're talking about source areas, the architecture of these source areas is really complex on almost every site. And I have an example there on the left. This is a carbon tetrachloride site that we got involved in, and we did some high density soil sampling, and we're able to 3D map the soil impacts. And so it's really hard to develop sort of a concise aerial and horizontally focused injection program without having that kind of information. So I think it's really important, especially when you're in source areas, to make sure you've got come in with something like the MIP on the front end, and then follow that up with some high density sampling to really get a good handle on the mass. Because I see a lot of sites that just fail just because it was just an unidentified source. And then secondly, it's going to be contact or poor distribution, which is really the focus of this presentation. All right, so the challenges we have, so first off, there are many reagents that are available that are on the market. And so, each of those reagents has sort of a box that it fits into, right? And this kind of ties in with the previous slide. You could probably have another bullet there of just poor reagent selection. It's really understanding the pros and cons of each technology and make sure you just stay within that box, right? So for example, if you had a technology that was mainly used for polishing, so let's just say like an oxygen release compound, which is generally used for really low concentrations, try using that in a source area that maybe has some LNAPL, and it's going to fail. You went outside the box, right? So we want to make sure that we're using the right technology or technologies. A lot of the sites we get involved in have combined remedies because we want to be able to leverage the positive attributes of each of these technologies without stepping outside of that. And so we want to understand the longevity because that's going to really be important from a design standpoint. Technologies last. If you go on the really low end, talking about hydrogen peroxide, it could be on a scale of minutes, right, to hours. On the other end, something like zero valent iron could last decades. And so really understanding the longevity, dosing as well. And that ties in with your conceptual site model. And also understanding that, technologies have lower and upper limits as to what you can apply. So for example, something like, say, sodium persulfate, which, it's generally applied in, say, pretty low single digit concentrations by weight up to, say, maybe 15-20% would be a pretty concentrated dose. Once you start going above that, it starts to break down on itself, and you also bring health and safety concerns in. On the slurry side of things, you run into slurry density issues to where you have to make sure that you can actually pump this stuff into the subsurface. And then lastly, again, contact, which is really what we're going to be, focusing here today. And I would say, an observation from, doing this for over 20 years is that a lot of the designs that come across my desk have unrealistic expectations with respect to things like injection point spacing, injectate volume, and others as well. And so this is really where pilot testing can be a separate event, or it could be just attached to the full scale. So you're going to take your first 2-3 days of a larger injection effort. You're going to use that as your pilot test to help fine tune your injection program. So I'd say injecting, those of you that have been out on injection projects understand that it is difficult. It's not easy. We're not all working in sandboxes, right? And so, it is difficult. And the field implementation plans, need to be flexible. And that is going to tie in somewhat with, injection wells versus direct push. If you're using all wells to inject your reagent, you don't have that sort of flexibility that direct push gives you. And lastly, direct push injection isn't always an option, and that's really, goes back to that situation where we get shallow refusal above competent rock. And so another challenge that we'll talk about when we get to that pre-drill piece of the presentation. So looking at liquids versus slurries. So liquids, again, we're talking about things like chemical oxidants. So things like hydrogen peroxide and persulfate, permanganate. Emulsified vegetable oil also falls into this category as well. And these are generally done under low pressure, low flow conditions, trying to go high volume, say, without, inject a high percentage of the pore volume. There are a couple strategies that we'll kind of talk about later when it comes to different trying to attack it from either a high percentage or a low percentage of the pore volume. And I would say DPT screens when you're injecting liquids generally going to vary from, I'd say, 0.3 to 1.5 meters. Your injection wells are going to be, say, 1.5 to 3. In general, if you've got I would say if you've got a thicker interval to treat than that, I would definitely nest wells versus having a longer screen than 3 meters. It is difficult, however, to target low K zones using this approach. So based on your conceptual site model, if the bulk of your mass is, say, in a low K zone, then low pressure, low flow may not be the best option. So look at slurries. These are things like activated carbon, zero valent iron, EHC from Evonik. So these have to be done under higher flow rate, higher pressure conditions, because you're trying to push a solid out into a solid, right? And just a note about pressures. So when we talk about injection pressures, and if you go out onto an injection site and you're looking at a pressure gauge, whatever that pressure is at the surface, at the injection system, that's the system pressure. That's not your downhole pressure. So you need to, what I recommend is to, once you get your site all set up, ready to go, take your injection tip and stick it in a drum and run at your, the flow rates that you believe you're going to be using, and see what the pressure gives you. Because obviously, it's, zero coming out whenever it's, above, that injection tip is sitting above ground. We have zero at the tip. So it gives you an idea of what your total system pressure loss is. And that could be significant. So it's something good to do is subtract that out of what you're seeing on the gauge on the system. And that gives you a better handle of what your downhole system pressure is. In general, we're using direct push for slurry injections, but we're using a different kind of injection tip. So we're using a jetting style tip that you see there in the lower right, where all your injection ports are in one plane. And so if you imagine, what's coming out of a pressure washer, it's going to be very similar to that. So the one difference between this approach versus liquids is that you're not going to be limited by geology. Now, your designs change quite a bit, and we'll discuss that later, whether or not you're in a low K or you're in a high K environment. So your, things from your injection spacing to your volume, your flow rates, your ejection tip itself, all of those can vary depending on the situation that you're in. So here's where I'd say you definitely don't want to use injection wells. So injection wells, again, based on your conceptual site model, understanding where the mass is, especially that saturated mass when you're working in a source area, is really important, because in general, most of the mass is not in those high K zones. It's either been degraded or it's already moved on, right? And so this was an actual site that I worked on last year, and client wanted to propose using injection wells, and I reviewed the data, and all his mass, all the saturated mass was tied up in these silt zones and below where they had done an excavation, and they wanted to put an injection well in spanning all these different horizons. And as you can figure out, I'm sure all that reagent is going to go into those higher K zones, and you're not going to get even really much diffusion into those lower permeability zones. So this would be a site definitely where I would look at more focused direct push applications. This is actual data from a site where we came in and did some work after a low flow, low pressure application was done. So on the left, you see here, there was, I blocked out the reagents that were used, but so there were 3 applications of a certain reagent, all done under low flow, low pressure. This was a permeable reactive barrier application. This was done in 1 row of injection points, which is, I'll come back to that later in the presentation. It was done all in 1 row of injection points, really limited number of injection intervals as well. And, they really didn't have good results. They had some increases. The data was really noisy. They had some increases here. And so we got involved at this phase here. We did some additional characterization using high res, as well as some high density sampling, and came out and did 3 rows of injection points, injecting a slurry And we added quite a few more injection intervals as well. And this was a pretty tight formation, and we were successful. The units that you see on the left, that's the total BTEX and the PHC concentrations. So that pre-drill technique that I mentioned that we've used quite a bit here in the States, and we've used it on a number of sites in Australia already. So again, this is sites where we can't use DPT by itself for various reasons. And so what we're going to do is we're going to pre-drill each of these locations using whatever the most economical approach is, whether that's augers, air hammer, sonic, to get down to that, whatever our design total depth is. We're going to backfill that with hydrated bentonite. We're going to build that in lifts. And then we're going to come back down through that with direct push. And again, using the high energy slurry injection. So again, going back to our injection tip here, we're using this style of injection tip. And so you can imagine, again, kind of a pressure washer coming out of those ports. That's going to slice through that bentonite and get out into the native material. And one note on this application technique, I would only recommend this for slurry applications. I would not recommend this for liquids. So if you went in and tried to use a low pressure, low flow application using this technique, you just path of least resistance, and you back up that borehole, and you're just going to squeeze all that bentonite out to the surface. And so to date, we've completed about 50 applications so far. And again, a handful of those have been in Australia in the last year and a half. So when it comes to bedrock, the key to bedrock is, really understanding, obviously it always comes down to the conceptual site model. It's a little more challenging on a fractured bedrock site. So we're using downhole geophysics and packers to, identify those samples first using the geophysics, sample those fractures to see what the contaminant load is. And then I would always recommend pilot testing. You can use pilot testing here, again, using the straddle packers to even inject water. And that really will help you understand your connectivity between your adjacent monitoring wells or injection wells. And I like using pressure transducers in this situation because you can pop those in, because your radius of influence is going to be much higher on a bedrock site than on an overburden site. So drop transducers into all the wells that are in the area. That really helps you understand the connectivity and what your radius of influence is, because the drilling of the injection wells, when you do ultimately get the full scale, is going to be a huge part of the budget. And so we want to be able to, minimize the number of injection wells that need to be installed. And lastly, just from a health and safety standpoint, not all reagents, and specifically chemical oxidants, are not going to be compatible with all packers. So just as from a safety standpoint, something like sodium persulfate may not be compatible with the packers you're using. So make sure that you go through that process to make sure that what you're using is going to be compatible. All right, so we'll talk about just injection design basics a little bit. So what are the variables that we can play with whenever we get onto a site? So first off, we can play with the grid spacing, play with our injection volumes. We can play with the actual injection tips themselves, the geometry between the different tips, excuse me, and also with our injection flow rates and pressures. And so when we're laying out a grid application, so this would be for either source area applications or for, say, dissolved plume applications, we're generally laying them out in a triangular grid pattern, and that spacing is going to be a function of a couple of things. Depth below grade, so that the shallower your injection intervals start, the tighter the spacing needs to be. And it's going to be a function of the geology as well, to a certain degree, but also your site constraints. And so if you're out on a site that has a lot of utilities, for example, or if it's, if you're working at a UST site and you're working close to the USTs themselves, you're going to want to go on a tighter injection spacing, at least in that area, because the tighter the spacing, the lower the volume, the less chance you have of short circuiting that material outside of your design radius of influence. And I would say for most DPT applications, you're looking at about 1.5 to 4 meters between your injection points. And then as to, actually when you're out there, how do you actually progress? How do you start, what injection points are you going to do first? I tend to work, outside in, because, you're putting a lot of energy into the subsurface. And if you're, moving some of the contamination around, you want to make sure that at least, you've got material on the edges to be able to, react with that groundwater. And say, or another way to do it would be, in this example here with groundwater moving up on the slide, I'd go in and say, do these 2 rows here on the most down gradient edge first. And that puts a reactive barrier wall in to be able to, again, kind of limit any mass flux of any contamination that could potentially move in that direction. So PRBs, we do quite a bit of these, sometimes by themselves, sometimes in conjunction with some source treatment. And so I would say it's based on our experience, we're injecting always on multiple rows of injection points, regardless of which reagent we're working with. Because ultimately what you're trying to put in place is what you see there on the right? So that's your perfect case. You're trying to replicate what you would do if you were going to trench this product in the ground. And it's hard to do with injection points because the distribution is not going to be as good as what you see there with a trench application. And so we want to have multiple rows of injection points to give us the best chance of limiting that mass flux moving off site. The injection point spacing in this situation is usually going to be a little tighter. I'd put that at 1.5 to 3 meters. So injection volumes are highly variable, obviously depending on the chemistry. Some chemistries are designed for really high volumes. So again, looking at things like chemical oxidants or emulsified vegetable oil, versus things like slurries, which are going to be lower volumes. When you're looking at liquid injections, I'd say there's generally two approaches. There's high volume, high pore volume injections. And those are going to be typically lower dosages, just higher volume, trying to fill more of the bathtub. And so you're relying there in less on advection and dispersion. Flip side of that is you can go with a higher concentration and rely more on advection and dispersion. And so that first case, that high volume, obviously is going to take more time from an injection standpoint, but I feel like your chance of getting distribution is going to be greater than relying on the advection and dispersion to transport your reagent in the subsurface. As I mentioned, slurries are going to be generally lower volume than what you're going to see with liquid reagents. But again, your pilot testing or your full-scale startup is going to assess that proper volume. And so we usually go in with, based on our experience, we'll come in with a design volume. But again, that may change, it may increase, it may decrease, depending on what we see once we actually put some material into the subsurface. So I need to apologize. I think my whole presentation has been converted to metric, except for these slides because they came from my office. So I apologize, but these are just examples of different injection tips. So that's that jetting style. And this is that trying to match up your injection tool that's in the subsurface with the geology. And so I would say what's more important is when you're working in coarse grain geologies, so sands, that when you're working with slurries, it's kind of somewhat counterintuitive. You have to put more energy into a sand site than I do for a clay site. And that's because the sand wants to filter out your reagent, right? Again, you're trying to push a solid into a solid. And so we tend to go with higher energy injections, higher velocity injections when we're working in more higher permeability lithologies. And so you take your injection flow rate and you divide that by the total area of your injection ports, and that gives you an exit velocity coming out of that injection tip. And so we have rules of thumb that we like to use where we like to match up, again, depending on the site, we like to match it up with the proper downhole injection tip. So you see here we have examples from 4 holes to 6 holes to 14 holes, all with different diameters. And here's an example of a soil core that was taken. This was at a pretty sandy site, and so you can see here this was about 3 meters away from the injection point, and you can see we've got a nice spread. This is with an activated carbon product, and you can see here we've got about a foot or so of material. And this is, again, so as it moves away from the injection point, it is gonna come out in sort of a V shape. And so the further that it goes away, the more of the vertical distribution that you're going to get. So one of the things that whenever we go out into a project, this is kind of falls under the QC category, is looking at the pressure signatures. And again, this is for slurries, but this applies for liquids as well. And so if you're injecting into a clay, for example, you should see a very distinct fracture pressure where you see your pressure increase, and then you're going to see that pressure snap down. Call it fracture pressure. We call this second pressure, this more flat pressure that you see here, as our propagation pressure. Once you cause the soil to fail. And so here's a couple cores that were taken out on a clay site where you can see the specs. This was an activated carbon application, and here's another core as well. So it looks quite different than the previous slide within a sand, there's another site here on the right-hand side. Pressure signature in a sand is going to be quite different. You're going to see that ramp up over a longer period of time, and again, it is going to flatten out, but you don't see that distinct fracture that you do with a low permeability soil. So looking at the pressure signatures when you're out on a site is really important, because you have an expectation when you go out based on your boring logs, based on your conceptual site model, and that all should jive whenever you get out into the field. So if you are expecting more sandy geology, and you're seeing a fracture pressure that I'm showing here on the left, then that's a point where we need to sort of take a step back and make sure, again, that we're using the right downhole tooling, or using the proper flow rates and pressures. So some more slide here just to talk a little bit more about field QC. So besides that pressure profile, we're looking at the water levels and see how those change as we're doing injection. So we can do that with a water level meter, as you can see there, the picture in the lower right. Or again, if you can rent some transducers and pop those in the wells, and then you can download all that data to see, as you're doing your injections, how that's influencing the water table. That gives us a handle on where we're getting influence. Implants are really temporary monitoring wells or temporary monitoring locations. And these are really, I like to use these when we have a really long monitoring well screen. So anything over 3 meters, if our injection interval is longer than that, and our monitoring well is longer than, say, 3 meters, then I like to put in these temporary implants just to be able to, get more vertical information on the influence. And then lastly, depending on the reagent that you're using, if there's a distinct color change, then you can do some soil borings to be able to assess the distribution that way. One way that's not mentioned on here is if you're doing something that's going to cause an increase in the electrical conductivity of the groundwater. So again, something like sodium persulfate, you can even use electrical conductivity probes as well to be able to assess that distribution. Okay, so we'll go through a couple quick project summaries here, and then we'll go ahead and open it up for questions. So here's an example. This is one of our first full-scale pre-drill applications, and our client went out before we got out on site, and each of these flush mounts that you see here, these were all the pre-drilled locations that use sonic, went down to competent bedrock, and then we came in with direct push and pushed through that bentonite to do the application. So we did several phases, pilot test, and then two phases of full scale. And the site has actually since gotten a no further action letter. So it's in the northeast U.S. This site, if you see the picture here, so this is it's a gas station that is next to a major highway. They brought the grade up for this gas station using the blast rubble and debris from putting in the highway, and so direct push was not going to be an option. And so that was the reason why on this particular site we had to use the sonic on the front end. There's a wetlands that sits on the up gradient side to the north here that we were trying to protect. The source area sits here where MW204 is. Our pilot test was in this area here, MW205. This well was abandoned since the full scale really consumed this original well, so we put a new down gradient monitoring well in MW207. So this was about 50 meters wide. We had close to 90 injection locations on a 2.25 meter spacing. The injection interval varied quite a bit, starting at about 8 meters down to 10 to 17, and that really depended on where they hit competent bedrock. So here's the data for this site, close to 2,000 days of data, and this was one application. And so the blue line represents that MW204 up gradient well. So these are the concentrations that were fluxing into the barrier. They varied between, say, quite a bit, say generally between 500 and 2,000 ppb total BTEX. And the orange represents, this was our the pilot test well, and this is our new down gradient well here. So we can see that we were able to successfully reduce that mass flux. Something that's not presented here, but our client went out and did compound specific isotope analysis as well on the site to be able to prove as a line of evidence that we were getting degradation out on the site. This was an activated carbon technology versus just adsorption onto the activated carbon. So here's another petroleum site, much higher concentrations. So this had Napple. This was a site in Finland that was done by our partner company that's based in Denmark. So they went in first off and went out and did a large MIP survey and followed that up with some high density soil and groundwater sampling to refine the conceptual site model, and determined there was about a 1,200 square meter area. Injection depths, it was about a 9 meter thickness from 4 to 13, and that spacing was similar to the previous site, about 2.3 meters. And it was clay with sand layers from 2 to 11, and then transitioned more to a more consistent sand below that. So we took all the data that we generated from the high res and the sampling, and so this was a large UST site. Just to make that comment, most of our UST sites aren't this large, but you can see here some of the advantages of having direct push is, in areas you can see here there's some higher density of points, and a lot of this is just because of you're going to get daylighting. It's just kind of nature of the beast whenever you're doing injection work, and you do get, you still need to get your design volume in. And so you can bentonite that hole and offset and apply the balance of the reagent in the adjacent location. So the groundwater for this site, again, it's much higher. I'm just showing the benzene here. So the benzene concentrations bounced around quite a bit, but baseline concentrations were in double-digit milligrams per liter of benzene. This solid vertical line represents when we did the injection work. They came out and replaced the monitoring wells a couple times because they were doing some regrading out on the site. But over about a 5-year period, we were able to demonstrate benzene reductions, 92 to 99%. And this doesn't get done on all of our projects, but they went out, and since they had all that baseline high density soil profile data, they went out and replicated that next to one of the borings in the source area about 3.5 years later. And so we're able to demonstrate here that we were able to significantly reduce the saturated soil mass as well. So one comment about soil sampling, you know, you're going to want to make sure that you wait a little while, because it does take time for the mass to desorb out of the sorb phase, get into groundwater so that it can be treated. So if you are looking to do something like this, to do pre and post soil sampling, I would definitely wait on a scale of years to be able to do that. It's gonna take some time. So I think this is my last one. And then we'll open this up for questions. This is an interesting application. So this is a chlorinated site. So this is a Superfund site here in the US in the state of North Carolina. And this site was unique because the client asked us to angle drill a PRB underneath the creek, and I'll explain why in a minute. But they had about 200 parts per billion of PCE discharging into the creek. And so we went out and did a pilot test first, and then full scale was done over 2 phases, and it's currently still in long-term monitoring. But to be able to get a consistent angle underneath the creek, we had this custom foot made for the geoprobe. So that's it's a nice application for this, for this specific, but we use angle drilling quite a bit if we're working up against buildings, underneath roadways. If you've got overhead utility issues, it can help as well. So it's definitely a useful tool. So here's a cross section for this site. The source area is sat up on the hill up here where the A prime is. And through a series of vertical injection wells and nested wells, they were able to show that the PCE was dipping down into this weathered rock and discharging up into the creek. And so they had asked us to sit up here on this creek bank and inject on an angle underneath to be able to create a PRB underneath and be able to limit that PCE discharging into this gaining stream. So the RDC, or that additional characterization that I've mentioned on a couple of these, is a little different for PRBs, because in PRBs, especially when you're a good distance from the source area, most of the mass is going to be in the groundwater in those higher K zones. And so we put a series of nested wells in, called micro wells here, just in really small sub-meter screen intervals, to be able to profile exactly where the groundwater was. Another useful tool here it wasn't used on this site, but another useful application for the high-res tools. I really like the HPT for this application, and it's something that Jonas will cover at the workshops, but it really helps you identify where your transmissive zones are. On this site, we just did it with vertical wells. I still think it's good practice to take some soil cores, though. We did on this site. We took a few, because you're basing PRB designs on mass flux, which is groundwater, right? But you still, if there is a sorbed component, you need to be able to account for that in the design. And our monitoring points on this site were actually the stream bed piezometers. So these were sunk about 1 meter down into the stream bed. And so this is that image that I showed you before when I introduced injection PRBs. This is that same site. And so it's about an 18 meters here for this. This was just a pilot test. But this cross section, I think, is really good. I really like it. Our client pulled it together. Each of these hash marks represents a successful injection interval. And that was deemed by, if we got our full injection volume in and we saw no daylighting, and no surfacing. And so you'll see there definitely are some gaps here. But if you sum this up from a cross-sectional standpoint, we do have a solid PRB in place. And so the data for this site, so it ranged depending on the well from 100 to about 150 parts per billion PCE. And we did see some immediate decreases in PC 103, which is the one in the immediate, almost on the center line of our pilot test area. 101, which was, sat up here, took a little bit more time, but we hit our goal of 5 parts per billion starting at about day 200, and we've been able to sustain that for the duration of the project. So we're about 50 minutes in, so I'm right on time. So we'll open it up for questions. I did put the QR code here for the workshops in case you didn't catch it on the first slide. And there's my contact information below, as well as Matt and Jonas from Legion. So thank you for your time. Thanks to Matt and Jonas for inviting me to speak today, and open it up for questions now.
Thank you very much, Mike, for the presentation. Very interesting. A very good teaser as well for your upcoming presentation at the forum and these workshops. We start really getting the first registrations coming through. So yeah, you have this for all the attendees, the chat and Q&A options on the lower bar. So if you have any questions for Mike, please send them there. We'll wait a few minutes. Somebody rose their hand. There is a first question there, I think. David Gregory asked if there is a paper summarizing the pros and cons of each reagent. Do you know, Mike, like any good reference?
So I would say the best, I don't know of a single document that summarizes, but I would say the ITRC website here in the US is a really good resource, where they've pulled together guidance documents on several of the technologies that I mentioned. There are, for example, there's one on chemical oxidants, there's one on chemical reductants. And so that's probably the best resource. I mean, there are some books that have been published that are on, say, specifically chemical oxidation, but it's really broad. There's just there are so many technologies that are available. I just think that'd be a challenge. But I would definitely check out the ITRC. If you put that in, it's the Interstate Technology Council, Regulatory Council. Yeah, Regulatory Council. But you just put ITRC in, they've got maybe, I don't know, 15 years of guidance documents there that they've industry experts have pulled together. So that would probably be the best resource.
Yeah, I think they recently updated their document on in-situ injection. It's called Optimizing Injection Strategies and In-Situ Remediation Performance.
Yeah, we were actually part of that. So yeah, definitely. That's a really kind of expands on everything that we talked about today.
We got another question regarding if there are any plans for a workshop in Melbourne. I thought maybe really enough for the people there with the Eco Forum. So we're planning to host a session of this workshop there as well. But we will have Legion Drilling will have an exhibition booth at EcoForum. Mike will be there as well, presenting. And then we are arriving there on Monday, the Monday before EcoForum, and we'll be there also the Friday after the presentations finish. So if anyone is interested, like in a in-person meeting or a presentation for their team, you can just contact Mike or me, and we'll organize something if we have time. Another question, what time frame would you need to validate attenuation in a low permeability chlorinated hydrocarbon site following slurry injection?
Oh, that's a I mean, it would really depend on the for example, I mean, if you're using biological treatment, then or versus something, say, abiotic like zero valent iron or a combination of those. Another variable would be as if, an activated carbon based product is used. So depending on what those starting concentrations are and what the ultimate goal is, right? So if you're talking about a low concentration site, it's if you're looking at a relatively low concentration site, then usually I would say within a year. But I've worked on DNAPL sites that we've been monitoring for 3 or 4 or 5 years, but you're talking about starting with DNAPL concentrations. So we typically will use like a logarithmic sampling program where we'll sample much more on the front end, maybe 1, 2, 3 months, 6 months, year, and then maybe go to semi-annual sampling after that. But unfortunately, it's kind of a hard question to answer without having some more specifics, and it would be again tied to, really driven by how much saturated soil mass you have. That's really going to be, because how long is that saturated soil mass going to be feeding groundwater? And so if you have a tremendous amount of saturated soil mass, again, with either measurable or suspected DNAPL, then you're definitely looking at the scale of years.
Okay, thank you, Mike. We didn't get any other questions, and it's almost 11. So I think we can end the webinar here. Thank you again, Mike, for giving us this presentation, and thanks all the attendees for participating. Hope to see you in future events.
Yes, thank you, Jonas and Matt, and thanks everyone for your time today.